Hello. Is it on? Okay, cool. Welcome to one of the last sessions of today. So I'm going to talk about how we can run Python code written against the Beam API on Flink. And I have to get a few disappointments out of the way before we can start. So in the description, or when we submitted the talk, we thought we could finish a demo and have this running, but we don't have this running actually, but we're still working on it. And also it was supposed to be a few more people coming, but unfortunately today it's just me. But I hope I can still present some interesting stuff. So let's get started. What I want to talk about today is what is Beam, because I'm assuming that a lot of people know Flink, because this is Flink forward, obviously, but some people might not know about Beam, so I want to talk a bit about that. I then want to talk about the portability APIs in Beam, which is the components that we use for executing code written in a different programming language on an execution language that is written in another programming language, which is quite fancy. And then this is just the generic API. Then I will very briefly talk about how this is used in the Flink runner, and then I will outline some future work that we still have to do. Okay, this is horrible. So, what is Beam? How many people here have heard of Beam, actually? Okay, so a lot of people, actually. So I can do this a bit more quickly. So, to understand where Beam is coming from, you have to understand how Google and the open source big data ecosystem evolved. So, big data, a few people would argue, started when Google released the MapReduce paper, because this is also when the open source developed an open source solution for MapReduce, and then when all these companies, Cloudera, Hortonworks, and so on, they drove big data. But while the open source was working on MapReduce, Google, they kept working internally on their systems. So there is Flume, not to be confused with the open source Flume, but this is Flume Java, which is an evolution of the MapReduce APIs. There's Millwheel, which is their streaming system at that time, and a lot of other systems. And most of these systems, because Google, they internally, they did their thing. They threw out a paper, but people, they couldn't actually use these systems that Google was describing in these papers. So what people did, mostly under the Apache umbrella, is they developed open source versions of that system, of those systems described in the papers. But then at one point, Google, they changed their mind and they thought that they would also like to offer a system for users to use. And this was Google Dataflow. This was an evolution and a combination of all the stuff that they published before. And it was an API for specifying programs in streaming, for streaming and batch computation, and it was also a service where you could execute those programs. And then where all of this comes together is Apache Beam, because then one step further, Google donated, together with some partners, for example us, they donated this the API part, the SDK, if you will, of Google Dataflow as the Apache Beam project. And now there are also open source runners, or if you will, engines that you can use to execute Beam code. And Flink Runner is one of those runners, which happens to be very good. But I might be biased on that. But so, in essence, what Beam is several generations after MapReduce, and it's APIs that let you focus on specifying what you compute, where MapReduce was a very low-level system, and you had people build actually abstractions similar to Beam on top of MapReduce. But now Beam is the culmination of all of this, and it's batch and streaming at the same time, or you can use the same program to execute batch applications and streaming applications. And another interesting thing is there's a very clear separation between processing time and event time. So interesting bit is that all this modern thinking, modern like last 2 years maybe, about event time and watermarks and stuff was popularized by the Millwheel paper, which again was based on older papers, but currently when people think about that stuff, they think about mostly about watermarks in the context of Millwheel, and then in the Dataflow paper where they also expanded on this watermark concept. So that's an interesting historical tidbit, if you will. Currently, the vision for Beam is that people can use the Beam model, if you will, so the concepts of Beam, and they can write Beam programs in different programming languages. So that could be Java, that could be Python. Then those pipelines, we will get to that later in more detail, but they go to a common format for pipelines. Then there would be different runners for executing those pipelines. So that would be Google Cloud Dataflow, of course. There would be an Apache Flink runner, Apache Spark runner. But now there's quite a bit of runners. And then the difficult bit is, again, executing these different programming languages on these runners that are written in other programming language. And this is roughly what I want to cover later in a section. But now let's first look a bit more at the Beam model and what some of the concepts are, and also I will give you some examples of what Beam code looks like in Java and also in Python. So because I still have Python in my title, so I have to show some Python code. But we'll get to that later. So when you program a job or an application in Beam, what you do is you're generating basically a graph of transformations that goes from sources through some transformations, and that goes to sinks. So this is how the Beam folks usually show these graphs. Flink usually has it sideways, if you look at the Flink dashboard. But in Beam, this whole thing is called a pipeline. And the pipeline is made up of P transforms. So these boxes that we in Flink usually call operators, they are called P transforms. And we will see in a bit what P transforms there are. And these connections between those P transforms, if you will, they are P collections. So they are more a logical concept. So in Flink, where you have the data set which represents the result of an operation, but which is not actually there in memory or a data stream, P collection is the similar or the equivalent concept in Beam. So that's the basic concept of what a pipeline is and what the transformations and the stuff in a pipeline are. And Beam also has as a core concept these 4 important questions. And there's a very clear separation, let's say somewhat clear separation in the API and when you think about concepts when you look at these questions. So these questions are what are you computing? So what is the computation? Is it a summation, or is it some filter, or is it some aggregation? You have to answer where, which tells you where in time you are computing things. This becomes, as we will see, important in stream processing, because stream processing is processing of an infinite stream, as we all know, and the where question definitely defines basically what windows you have. When is the question of when you want these results to be produced? We'll see an example in a minute. And how is, sounds quite abstract, but how is the question of what happens if you have late data, or how do subsequent results of computations relate? So we'll see an example that makes this very clear in a bit. And now let's step through a little example where we try and answer all of these questions and also look at code on the way. So on top you see Java code. On the bottom you see the equivalent Python code. So this is actually working, and you can try this out using a runner different from the Flink runner, the direct runner. But what we're doing here is we have an input. So the input would be a P collection of some type. And then we apply a P transform. In this case, we want to sum them up by key. So what we're basically doing is counting stuff. And the equivalent Python code is given here. The Beam Python API uses the pipe character for appending transformations one after another. So in this case, input would be a P collection, and pipe would be applying that computation on this input. And you will see that we can chain these pipes together to form pipelines in the Beam Python API. And some people might have seen these before. These are these nice animations that showcase what the computation does. So here on the bottom axis we have event time, so we have these events that happen at different timestamps. The y-axis is processing time, and because we only specified the what we want to be computed, this is a classical batch computation. So we sum up these values and we have a result once we processed all the values. And we don't take into account event time, or we don't produce results before we have seen all data, so when we reach the end of the data. This is what we are computing. Then the next question that we answer is where in event time. And for this, we specify a window. So here we say we want to split our data into windows of 2 minutes. And we do the same for Python. And as I said, you can use this pipe to string together transformations. So here we have the window into followed by the sum. And what this then looks like is we now compute the sum, but based on these event time windows that we have. So we have a window every 2 minutes, and we still get the result at the end when we have seen all the data. So this would still be a batch computation, because we don't emit early data when we are somewhat sure that we won't see any more data for a given event time timestamp and so on, but we will get to it in a second. Now, so if we only have the what and the where, then we are still in batch territory. But as soon as we can specify a when, meaning when in processing time do we actually want to get results on this stream, and for this we specify a trigger. So here we say we want to get results for our computation once the watermark, which specifies how far in the stream we have progressed in event time, when the watermark passes the end of the window. So here we say we have a window, we say trigger at watermark, meaning when the watermark is at the end of the window, and we have the same for Python. So what we now get is still the same computation, but we emit results as soon as this watermark passes the end of the window. So the watermark is the wave that goes through there. And what we also see is there is this 9 up there, which is arriving late with respect to the watermark. So it doesn't influence that result anymore because it's dropped by default. And this is actually where the fourth question comes in, the how. So by now, this is becoming quite colorful, but we built this up slowly. So the how specifies how subsequent results for a computation of a given window relate. Because in this case, where we had this late data, we already fired the window, so we have a result for that window, but then we got a late event coming in, and we need to specify what to do with this late event. So in this case, we say, we specify that we want to accumulate firing panes, meaning that once the result is computed for the window, we keep that result, and in case late data comes in, we add that to the existing result and emit this as a new result. So what we then get is we are emitting our results as before, and we also count that late data. So that's a very quick tour of both the concepts and also of how they would be used in the Beam Java API and the Python API. But if you want to learn more about this, there's a link that you can go to which has a running example on that. And the slides are going to be available, so you don't have to write it down now, of course. And, of course, I also want to show you a complete example of a working Python example. So this is not word count, like the classical word count, but it's actually counting Twitter hashes. And what we see here is that in the Python API, we create a pipeline, which is this basic concept that contains P collections and P transforms. And then we build our transformations. So here what we do is we read something from PubSub, we specify our windows, we specify that we want to parse hashtags out of this, we say that we want to count these, and then we format this for outputting, and then we write it to BigQuery. So this is obviously a very Google-influenced example. So in a different system, you might be using Kafka for this, and HFS or some other key value store. So to summarize what Beam is, it is the Beam model where we have these 4 important questions. And it is also an SDK that allows programming applications or pipelines that use this model. And it is also runners for different engines for executing these pipelines. So as I said, there's the Dataflow runner, and an important other runner is the in-process runner or direct runner, which allows you to play around with Beam and execute stuff on your local machine. And of course, there's Cloud Dataflow runner. And these other runners, and there's more runners such as Gear Pump, there's now a MapReduce runner coming up, and other stuff. So now let's go to the portability APIs. And to understand why we need these portability APIs, we have to take a step back and actually look at what we are trying to achieve. And the basic problem that we have to solve is that we have a runner, say we have the Flink runner, which can execute pipelines on Flink, which is written in Java, and we have a Beam SDK, for example, for the Python language, where users write user functions in Python. And we have to somehow bridge this gap between user code that is written in one language and a runner that is written in a different language. So this is the basic problem that we are solving in our work. And an important thing is also that in this context we are talking about Python, but actually all these portability APIs and the concepts, they are not specific to Python. Actually, I'm not a Python programmer. I could write Python if I had to, and I can read it, but I would not be good. But the good thing is that I'm just working on these generic APIs, and then it just works on Python because other people are writing this Beam Python SDK. But if there's in the future an SDK for a different language, then this will also just work with the Flink runner because we have these generic concepts for that. That we'll see in a second. But before we start, we also have to get some terminology straight because I might be using those words. So the Beam model, I have already said that, is it's a description of what a pipeline is, of these P collections and P transforms, and it's also a description of the operations that you can perform on P collections. A pipeline is a graph that is defined by the users that consists of P collections and transformations. And how this pipeline actually gets constructed is by a user using an SDK. So a Beam SDK is a language-specific API or library that implements the Beam model for a specific language. So if you write Java, you would write your program using the Beam Java SDK. If you write Python, you write it using the Beam Python SDK. User-defined functions, obvious, it's code written in a language like Java or Python. In Beam, there's not many different user-defined functions. There's basically only the do fun and the combine fun. In Beam, we call all these functions, we call it fun, fn. So do fun is basically a flat map, and combine fun is like a supercharged reduce, if you will. It's a combine and reduce combined into one. So these are the only two basic user functions that you can have in Beam. And last bit, a runner is the bridge between the SDK or a pipeline written by the user and the underlying execution engine. So the Flink runner can take a pipeline and execute it on Flink. This is the big picture of what happens when we want to execute a pipeline on some runner. So in the lower left, we have a user, say, and they would write a pipeline using an SDK. So all these clouds, they are APIs or SDKs in this figure. So they use an SDK, and the result of this SDK is a pipeline. Or the result of using that SDK is a pipeline where the user specified their transformations and their collections and their sources and their sinks and so on. Then the SDK uses the pipeline API, or if you will, the runner uses the pipeline API to somehow translate that pipeline to a job that can be executed on the underlying execution engine. So Flink would take the pipeline and transform it, for example, to a data stream program or a dataset program so that it can execute this on the Flink runner. And then that's where a Flink specific part sits. And then for executing this on a cluster, so a different number of machines, we have a Flink worker, say, and we have our, in this case, Python code. So this is obviously, it's the map function of a word count example. The people in the back might find it a bit small to read, but this is the user code that we have to execute. And a worker, so in this case, a Flink operator would use the fun API to communicate with this user code in a defined way. So we get in a second to how that actually works. And then the last bit is the job API. This is an API that can be used by the user to control execution of a job. So it can be used to start a job, it can be used to query the state of the job, so is it running, is it cancelled, and it can be used to query metrics of the job. So these, the pipeline API, the job API, and the fun API, these are the portability APIs. And I already hinted at some of this stuff, but the pipeline API is used for communicating what a user-specified pipeline is, and for communicating this to a runner. This is what the pipeline API is for. The fun API is for communication between the runner and a user-defined function written in an arbitrary programming language. And the job API is for interacting with a running application on an arbitrary runner. So we'll investigate these in more depth now. So that's just a high-level overview. So the pipeline API is actually it is a set of protobuf definitions that define the components that can be in a pipeline. And the pipeline API also defines the primitive operations that can be in a pipeline. And in Beam, there's actually a very small number of primitive transformations. There's only read, which is sources. There's pardo, which is a flat map. So pardo takes a dofun as a user function. There's flatten, which is union, a union operation. There's window into, which is the operation that assigns windows to elements. And there's group by key, which is the shuffle implementation. So group by key or a combine. That's happened all under the umbrella of this primitive here. And in a simplified way, a pipeline, this protobuf definition, it consists of the number of P collections that are in this pipeline. It consists of the P transforms that are in this pipeline. It consists of the windowing strategies that the user used in their pipeline. And it consists of the coders in the pipeline. So coder is the equivalent of Flink's type serializer and type information. And this is what is used for serializing events when sending them between operations in the pipeline. And this is also what is used, for example, for serializing data when you send it over the Fun API to user code written in a different language. And the interesting bit here is p-transform. We can delve into this a bit. So p-transform defines what the inputs and outputs are. These are p collections. And it defines a function spec. And the function spec is a URN, a resource name, and a payload. So the URN would say what type of user function this is. For example, it could be a pardo, or it could be a do fun, or it could be a combine fun, or some source. And the payload is just bytes. And the payload can contain, for example, a serialized Java function, or contain a Python function, or whatever other programming language we might have. Then we quickly outline the job API. So the job API, as I said, allows you to get the state of the job, so running or failed and so on. It allows you to cancel the job. It allows you to wait until the job is finished, and it allows querying the metrics. So this is all there is to the job API. Oh, and by the way, in case you haven't noticed, here in the bottom, there's all these links to design documents. Here, we lay out in a lot of detail the design of these APIs and the thoughts between why these APIs are as they are. But for a job API, there's no such design document because it's too simple, actually. Now we come to the Fun API, and this is actually the most complex piece of the portability APIs. And what the Fun API essentially is a set of gRPC service definitions and definitions of how data can be sent between services. So gRPC is an RPC system initially developed by Google. It's open source. And here, no surprise, you use protobuf to define data types that you can send between services, and you also define different services. And gRPC can then go on and generate code for running a server that can offer such a service, and for running a client that can connect to such a service. So then you can, for example, generate Java code for, say, running a specific service, and you can generate Python code for a client that connect to such a service, and then they can communicate by serializing data using protobuf and sending this across the wire. And the Fun API defines 4 services, or 4 planes, if you will, over which you can send data. There's the control plane, which is used by a runner such as Flink to tell the harness, which is executing a user function, what data it should be processing. So this is for controlling execution. There's the data plane, which is moved for actually sending data to the user function and for getting results back out from the user function to the runner. There's the state API, which is used for accessing state in the user function. So Beam, similar to Flink, has APIs for accessing keyed state, or for setting timers, or for firing timers. And Beam also has support for side inputs, for example. And this all goes over the state API. And then there's an API for logging. Because if you run user code in some other process, maybe because you run Python, it runs in a different process, you still want to get the logging output of that user code somehow back to your runner, in this case Flink. And this is what the logging API is for. Using this, a user function can send log output to the runner, and then the runner can send it to whatever logging system is configured for the runner. That's a quick figure that outlines what components we have here. So we have the runner. In this case, for example, it would be Flink, and the runner is responsible for keeping track of state, keeping track of timers. It's responsible for the metrics. The runner it's receiving data and sending data across the network. And I quickly mentioned this. The harness is the component responsible for executing user code. So for example, if there's a Python SDK, then this also comes with a harness that can be used for executing user functions, because this is what the runner needs to execute those user functions, and the harness would be started by the runner, and then the harness would communicate via the Fun API with the runner, and they would use the control plane and the data plane to facilitate execution of user functions. And these are very colorful pictures from these design documents that I mentioned. So if you noticed, it's all different design documents. So at the end I have links to all these design documents, but overall it's roughly 5 for the Fun API, because it's a very big piece of technology actually. And so an overview of how it works is that the runner would talk to the SDK harness. So in this case, the runner would be Flink, and it would be written in Java, and the SDK harness would be some Python code running somewhere. In a second, we will get to how you actually instantiate that. So it would use the control plane to register any functions that it might want to execute. The harness would initialize these functions. It would initialize a connection over the data plane for receiving and sending data. The harness would be responsible for starting these functions, for sending data back, and here it's just processing elements. At some point, it signals the end of computation for that bundle of elements that the runner specified that it should process, and then it returns the result, and then the runner can output those results to a downstream operation. Now as a last step, we have to look at how we actually execute these functions. So this is the pipeline that we have, and say we have some p-transforms, and let's say we need to execute those 2 here because they are actually Python code. And now there's a very neat idea of how this actually works in the harness. So because we already have a specification of pipelines and sources and things, and we can execute these pipelines, what we do is we cut out these 2 Python functions from the pipeline. We insert some sources a source that would read via gRPC from a service, and a gRPC sync that would write to a service. So we do pipeline surgery, basically cut this out, change the sources and sinks, and then tell this Python SDK harness to actually run this code where the sources and sinks communicate with the runner via this defined RPC interface. So here, let's say we have our worker, and it's executing this code using this pipeline. And how we actually execute this SDK harness can be done, for example, by executing a Python process where we run this harness, or as is actually planned in this design document down there, is we have Docker containers for specific languages that execute these user functions. So what we would have is a repository of containers for different SDKs in different languages. We inject the user code into this container, and then we start a container, and it can start the harness, connect to the runner via the RPC interfaces, and get started on computation. Now actually on Flink, this is very simple, because what Flink has to do is just to analyze and transform this pipeline, has to create a Flink job, say dataset or datastream API. It has to ship the user code or the description of the Docker container. And then in an operator, it has to open these gRPC services so that the harness can connect to them. and then it can execute the code using the Fun API. And this is actually this easy because Flink's operator in the streaming API has these functionalities for state and timers that map very well to Beam concepts. And that's actually why it's very easy and why the Flink runner is probably going to be for a while the only runner that can support these portability APIs and can support these different these pipelines written in different languages. Let's finally look at what are some of the advantages and disadvantages of this approach. So the advantages are that executing code or user code in a different process or even a different container leads to excellent isolation between user code and the system code. It also means that because these containers, these Docker containers can be user specifiable, they can exactly determine what the execution environment should be. So they can define the libraries that are available there, the Python dependencies, and so on. And we can mix code written in different languages. So we can, for example, when you use Python, we can use the Kafka source written in Java. We can have a user function written in Python, and they all work together in one job. And the disadvantages is that this is quite a bit slower because gRPC introduces quite some overhead because state access, sending data, receiving data, all goes over this RPC layer. And of course, if you want to use Docker, you have to use Docker. So that means you introduce an additional requirement for Flink. So you will only be able to use this on machines that have Docker available. So quickly, what is the work remaining on this? So first, of course, we have to actually finish all the stuff that I described. So we are planning to finish this by beginning of 2018, but don't quote me on that, but that's what we're hoping for, actually. These portability APIs, there's still some work ongoing there. So for example, the state API was only landed very recently in there, and there's still some stuff that you cannot do over these fun APIs that you can do with normal user functions. I already mentioned that you can mix and match connectors in different language. And for me, actually, the exciting thing is that because once we have these portability APIs in place and we can execute Python code on Beam, once there is a new SDK for a new language, and there's a Jira issue for adding an SDK in the Go language, for example. Once we have that in place, once there's an SDK for a new language, this just works on the Flink runner as well, without us having to write specific code for dealing with Go, because we do it via these generic RPC interfaces. And as I said, so you can probably find these URLs, but the important bits is there's all these design documents for the runner API, which is the pipeline API, and the fun API, and for this container contract thingy that specifies how we deal with Docker containers. And if you want, you can join the mailing list, follow this. It's actually quite interesting what is going on there. So that's it. I think we have time for questions now.
Thank you. Questions?
How much slower?
So when we initially started work on this in Beam, the folks from Google, they ran some tests with an initial testing implementation on their service, and so talking about running it on the Google Cloud Dataflow service, and they said that they have roughly a 10 to 15% performance impact. But Google Dataflow already, it's different from Flink, the execution model, so because it is not crazy high throughput as Flink, the impact of these additional RPC layers is not that big. But for example, I have a prototype implementation of this where I execute a Java user function, but not by using just method calls, but by actually starting a Java SDK harness that communicates via these RPC services. There, if I run it on a local machine without network transfers and so on, then I get roughly a 5 times slowdown. But this doesn't have any networking and other effects. So I guess in a cluster environment, when actually running things, also when you have the Rocksby backend and other things going on, there's a different factor. But it is quite a bit slower. And also, just using Python, I would imagine that there's also a slowdown when you execute Python functions in these processes.
Any more questions? Thank you.